Hey, here we go. Trying this um, recording style out here. So, just going to do hopefully a relatively brief video on some review and push in the direction that we're going. So, hopefully, not too much new content here. Um, but as we wait to reconnect for our full weeks back together, uh, it's best if we don't lose our momentum and lose what we were talking about. Specifically, some of the complex number information. Certainly, at a first pass, it's going to be tough to pick up, and I know that was challenging. So, here we're going to start back a little bit, back with factoring, and we'll make our way all the way back to the complex numbers. So, with factoring, we are interested in a few things. Factoring shows us quite easily where our zeros are, right? Our zeros are where our function is going to cross the y-axis, cross the x-axis, right? It's when our y value equals 0, that's when the function crosses the x-axis. And so if we recall, the highest degree of our polynomial is going to tell us the general shape. The zeros help us place that shape onto the graph. Now, we're also going to be interested in our intervals, right? Intervals. So these are just our main vocab words. When is the graph positive? When is the graph negative? And how do we know? Well, we analyze by putting our zeros on a number line, choosing values in between our zeros, plugging those into our function, and seeing if the resulting number is positive or negative. Okay. And finally, we're interested in end behavior. End behavior. What is our graph doing at either end? Are we tending towards infinity, negative infinity? Is it asymptotic, right? Is there some boundary that this graph continues getting closer and closer to, but never reaching, right? So these three pieces of information are things that we are interested in while we are factoring, right? So let's just do one example here, and we'll do a basic example just to review. So maybe we have x squared plus 2x plus plus 1, excuse me, right? And we remember to factor here, if there's no coefficient in front of the x squared, we're just going to have x and x. We need to multiply to our last number and add to the middle number. And so you can see here, 1 times 1 is 1. 1 plus 1 is 2. And so here's our factored form. In this case, we have a double root, right? Both scenarios here, x plus 1 equals 0. Solve for x equals negative 1. So I've found my 0, and in fact, there are 2 zeros at the same spot. This we call a double root, And when we see a double root, we know that the graph doesn't cross the x-axis, it just touches the x-axis, all right? So this graph will not cross the x-axis, but it will just touch the x-axis at x equals negative 1. So we know this is a parabola, and it's just going to touch there at negative 1. I happen to know that the y-intercept is at 0, 1, but not super relevant for our purpose here. Right? So first, we've found our zeros. In this case, it's a double root. There's 1 0. this graph just touches the x-axis. It doesn't cross. Why? Because we've determined a double root, right? This and this expression are the same. So x equals -1 is our 0. Next, we would analyze the intervals of this graph. So the visual intervals of this graph. And to do that, we put a number line down and we place all of our zeros onto this number line. In this case, our 0 is just at x equals -1. And so we're curious. Everywhere to the left of this, for any input, for any domain values, for any input values to the left of -1, so less than -1, will the resulting function produce a positive answer or a negative answer? Now, visually, we can see on the graph up here that all of these outputs to the left of -1 are in fact positive, right? The outputs, the y values, everything when we input any value at -1 or less than -1, all of our outputs, our range, are all positive. And so this is going to be a positive interval, a positive interval. If we're not sure, if we don't know what the graph looks like yet, well, we can just take any value less than -1, let's say -2, and we're going to plug that into our original equation. So we could have -2 squared plus 2 times -2 plus 1. The resulting answer there is 4 minus 4, 0 plus 1 is 1, and that answer is positive. That answer is positive. That tells us that the interval for any input value less than -1, our output, our range, will be positive, right? And that dictates how we draw this graph. This should be above the x-axis. We're going to do the same thing on this side, right? Same thing greater than -1. We want to know on the interval where x is greater than -1, is our graph going to produce positive outputs, right? As we input domain values greater than -1, will our output or our range also be positive? Or will it be negative, right? Positive outputs will place that graph above the x-axis. Negative outputs will put it below. So we just choose a value. We could use 0, right? 0 is greater than -1. We input 0. We have 0 squared plus 2 times 0 plus 1, and we get a positive 1. So we know this interval is positive as well. It comes as no surprise. I've drawn the parabola already, and all the values except for the double root at -1 are positive, right? All outputs, all y values are positive. Okay. So let me just refresh here. Or we can just talk through this question one more time, right? So we're factoring. Why are we factoring? Well, one really helpful thing that we get out of factoring some polynomial is where that polynomial, where the image of that polynomial crosses the x-axis, so we can get the shape. And so we factor this basic polynomial, x squared plus 2x plus 1. We end up with a double root. This means that at the location of a double root, we just kiss the x-axis, just touch it. We don't go past it or through it. We just touch it when there's a double root. Next, we want to analyze the intervals, right? The intervals of the graph. Anywhere less than -1, below that 0, we want to know, is the function positive? Yes, it is. Anywhere greater than -1, is that function positive or negative? Right? That'll determine the shape. Finally, we can look at end behavior. Here is pretty clear, right? As our x values approach positive infinity, as our x values approach positive infinity, our y values continue to grow. So our end behavior here is that y approaches infinity, right? And we write it as a limit statement. We would say the limit as x approaches infinity equals infinity, right? The limit of our output as x approaches infinity equals infinity. Y continues to grow. Similarly, we can look at the limit as x approaches negative infinity. So this time we're interested in what happens to the graph as our inputs continue to get lower and lower. Well, in this case, again, y approaches positive infinity. So the limit as x approaches negative infinity is also infinity. Okay. Let's just look at a polynomial that's already been factored, and I'll just come up with this on the spot, right? This represents some polynomial. Okay. In this case, we know it's a degree 1, 2, 3, 4, 5, degree 5 polynomial. And so it's going to look something like either this, or it's going to look like this, right? Odd degree polynomials end up splitting directions, tending towards negative infinity and positive infinity on either end. And so just have this general intuition as we begin. This is a degree 5 polynomial with these general shapes. But first thing we do is analyze our zeros, right? For what x values can I plug into this polynomial to make it equal to 0, right? Those points are where the y value is equal to 0, right? What I mean here is for what x value will the graph cross, right? You can see our y value at that point will be 0, right? So our output is 0 where we cross the x-axis. All I need to do is make any one of these terms equal to 0, right? So x plus 1 could equal 0. In that case, x equals -1, right? If I plug in -1 here, it's 0 times something times something times something, but anything times 0 is 0, right? And so all we have to do is find out for what x values does each term equal 0, right? And so x could equal -1, x could equal 2, x could equal -7, and x could equal +3. Okay, what is this squared here, right? What is this squared here? Well, what it means is we have x minus 3 times x minus 3. And if you remember the last one, this looks a lot like it, right? X plus 1, x plus 1. Here it's x minus 3, x minus 3. This is what we call a double root. So it can come in this form here, or we could expand it out and express it in this form here. What we have is a double root, right? And so the graph is just going to kiss at that point. It's not going to go through the x-axis. It's just going to kiss, kind of rebound off the x-axis, okay? And so, well, here we go. We have the zeros. We know that this polynomial function, this graph, is going to cross the x-axis at points x equals -1, -7, +2, and +3, right? And so I can go ahead and put those on this coordinate plane. 3, 4, 6, 7, -7, -1, 2, 3. Okay. Now, as before, this is where we're not sure if this graph comes from below Remember, just kissing at 3, right? Because it's a double root. So we're not sure if it comes from below or if it comes from above. Okay? We're not sure which case we have. In order to figure out which one of those is correct, we do some interval analysis, right? How do we do that? Well, we have our roots. These are where it crosses or touches the x-axis. And then we just need to determine, for any value less than 7, is the function positive or is it negative? So we pick a value, maybe -8. We plug that into the original string. We have -8 plus 1, so that would be -7. -8 minus 2, that would be -10. -8 plus 7, that would be -1. And then -8 minus 3, that would be -11 squared. Right? So we'd have a negative times a negative times a negative times a positive. And that is going to result in a negative value, right? Even number of negatives will multiply to positive. An odd number of negatives will multiply to negative. So we learn this interval is negative. For any value less than 7, we're going to get a negative result. And so that tells us we start down, right? Our graph starts from below. Okay, that's what it tells us. Now, we're going to assume, as this graph comes up, we know we have a 0. We have a place where it crosses the x-axis. It's coming from below, so we're going to assume this is going to come up, right? It's going to be positive here. We can double check that by choosing a value between -7 and -1, maybe -2, just for simplicity's sake. And we plug that into the string, right? We plug that into the string. So if we plug in -2, we're going to get -1, -4, +5, and a positive, right? It's going to be -5 squared. So that's a positive number. So we have negative times negative times positive times positive. That's going to be a positive value, right? Negative times negative is positive, times positive, still positive, times a positive here, still positive, right? And so, ta-da, right? As we assumed was going to happen, we end up in positive territory. This interval is above the x-axis. This interval is positive, right? Now, we can continue on checking each one, but I'll tell you, this one's going to go negative. It's going to come positive. It has to come back down and touch 3, but since it's a double root, it bounces. Okay. So you would find that actually the interval between 2 and 3 is positive, and the interval here is also positive. So we go negative, positive, negative, positive, positive, okay? If there is no double root, generally, the signs continue to switch off from a negative to a positive to a negative to a positive. The double root kind of blocks that. The double root bounces us back and keeps us in positive territory. So we have negative, positive, negative, positive, boom, double root, bounce, stay in positive, okay? Again, why do we care about analyzing our intervals here? Well, it's because it shows us the actual image of our graph, right? Before we analyze the intervals, we don't know if this graph is going to start from above and come below, all right? Now we do. And this blue checkered line is our final answer. Okay, so that's kind of the overview there of not how to factor, but why we care and what we do with our factored information. We get our zeros, we analyze our positive or negative intervals, and yeah, almost forgot, we analyze end behavior, right? And so we ask the question, as x approaches infinity, so as our input values continue to grow, what happens to our y values? Well, the limit as x approaches positive infinity equals infinity, right? Our y values here are going to continue to grow. We'll analyze the end behavior on the left as our x values approach negative infinity. Well, you can see our y values also approach negative infinity. So we can say the limit as x approaches negative infinity equals negative infinity, right? Now, I don't think you have to worry so much about this notation yet, but it's coming, so you might as well get used to it. Okay. Take a pause there for a second. There's our factoring, right? Factoring. And we moved on to looking at geometric series. Geometric series, right? And sequences. If you'll remember, a series is just simply a list of numbers. A sequence is taking that same list of numbers but adding them all up together, okay? There are many kinds of series and sequences, but the elementary ones, the ones that we are interested in, are geometric and arithmetic. Arithmetic, those are built by adding the same number to the previous number each time. But geometric series, those are created by starting with a given number and choosing a new number to multiply by the previous number each time. So maybe our first number is 2, and we decide, okay, for every result, we'll multiply by 3. So it goes to 6, right? We apply the same geometric ratio. So we go to 18. We continue multiplying by 3. And this is how we build, okay, 162. And this is how we build our series, right? This is simply a list of numbers. You could be given this list and you could be asked, what is the geometric ratio? Well, in that case, the answer would be 3, right? 3. You need to multiply each next number by 3 to get your, multiply each previous number by 3 to get the next number, right? You could be asked, what is the first number? And of course, you just look at the first, right? Always denoted A. sometimes A1, right? Our first term is 2. Our R value is 3. That's our geometric ratio. And sometimes we have N. This just tells us how many terms, right? How many terms, right? Of course, we could continue this series to infinity, right? We don't have to stop this. And so in that case, N could equal infinity, right? But sometimes, maybe you're building a stadium and you have, I don't know, 10 rows of seats, right? And so N equals 10. You only want to create or produce 10 numbers in your series or sequence, right? So we are allowed to restrict that however we see fit. N equals 10. We just want to go 10 terms, right? And so as far as indexing or labeling, we have A. A1 is our first term. We could say A2 equals 6. A3 equals 18. A4 equals 54, and so on, right? A refers to a specific number within the series. Generally, if A is just on its own, just A, it's referring to the first one. We have R, that's telling us how rapidly we grow, right? In this case, the geometric ratio is 3. And N, how many terms do we want in our series or sequence, right? We can let it run, and that N can be infinity. We can restrict it to something that we want, any number, perhaps N equals 10, right? Just 10 terms. Okay. So we looked at 2 formulas. And so I'll just create a new page here. Just stick to the same sequence, same series. Okay. Okay, maybe I'll write this down. If you want I should say the Okay, so if you want to know the specific value of any specific term, you use the following formula, right? So if I can say it in another way, if you want to know what's the number at, the 100th term, or what is the number that is produced at the 12th term, right? You can imagine, okay, I just keep multiplying by 3, keep multiplying by 3. And if I want to find the 12th term, I think that's possible, right? I could just do a few more calculations, and pretty soon I'd be at the 12th term. It'd be pretty big, but I could get there. But what if I asked you to find the 100th term, right? That would be a lot of calculating, right? You got to make no mistakes. You have to make sure that you choose the 100th term. It's kind of impractical to simply use a calculator or a pen and paper. And so we have a formula, a nice convenient formula that says, oh, so you want to know the value, A, of any term, N, right? Of any term. So if N equals 1, right, that means you want to know the value of the first term, 2. If N equals 10, right? That means you want to know the value of the 10th term. I don't even know that, right? I'd have to do some calculating. So the formula starts with, okay, you want to know the value of any term indicated by n. You get to choose. To find that, you simply take the first term, multiply it by your geometric ratio, and raise the ratio to the n minus 1 power. Okay, so if I want to know the 10th term, I would say, I want to know what the value of the number is in the 10th term. That's equal to the first term times this geometric ratio raised to the 10 minus 1 power. That's equal to 2 times 3 to the 9th. And what is 3 to the 9th? Let's see. Ooh, I don't have my handy calculator with me here. 3 to wow, equals 19,683. Times 2, and we're left with, well, our 10th term in this series is 39,366, right? So we've gotten pretty high in just 10 terms, and you can imagine using a pen and paper or, muscling through just hammering on the calculator. And it might take a while, but using this formula reduces pretty quickly. Of course, you can see that we're going to have high exponents here if we want to know a far number in the sequence. And so you do need a calculator handy unless you want to leave your answer expressed as an exponent, right? Maybe I could leave my answer expressed as 2 times 3 to the 9th. Maybe that's okay. But there you go. There's a nice formula you want to use if you want to know the specific value of any specific term along the way in a series. I'm kind of using series and sequence interchangeably. Sometimes I even get confused. Series is just a list of numbers. Sequence is when you add them all up, right? Add the first 10 terms or something. And that's what we'll look at next. So the next formula tells us how to sum the first n terms in a series. Again, n is the number you choose, right? If you want to sum the first 2 terms, then n equals 2. If you want to sum the first 100 terms, n equals 100. The formula we learned for that is the sum of the first n terms is equal to the first term times 1 minus our geometric ratio to the nth power divided by 1 minus our geometric ratio. Okay, and so let's see this in action. We can stick with the same series, 2, 6, 18, 54. Maybe we will look at it again for the first 10 terms, right? And so the sum of the first 10 terms of this sequence, right? 2 plus 6 plus 18 plus 54 plus 162 plus all the way to the first 10 terms is equal to the first term times 1 minus our geometric ratio, 2, that 10th power, divided by 1 minus our geometric ratio. So we have 2 times 1 minus, okay, let's see if we can get a nice answer here, 3 to the 10th. Divided by negative 2 equals 2 times negative 59,048. Yes. Divided by negative 2. You can see we're going to have a negative divided by a negative. The 2's actually cancel out here. The 2's will cancel out. And so we're left with 59,048. So if we take the first 10 terms of this series and we add them, we sum them, we're going to be left with 59,048, right? When might this be relevant? Well, I kind of always fall back to this stadium seating kind of one, right? Maybe in the first row of your stadium, you just have 2 seats. In the second row of your stadium, you have 6. And you continue to grow by a factor of 3. And you want to know how many seats total after 10 rows. Well, if you grew in this pattern, right, you would have 59,048 seats, right? Maybe it's more appropriate to think of it as far as like a rabbit population growth or something, right? One rabbit, or you start with 2 rabbits and they each have 3 kids, so they have 6 now, and the population grows in that way. But anyway, if you want to know the sum of the first n number of terms in a series, we use this formula, right? Okay. Now, just to say, geometric series, these are exponential series, right? And so oftentimes they do grow exponentially, faster and faster and faster and faster. You can see that happening with that last series, right? We go from 2 to 6 to 18 to 54, and it starts growing really rapidly, right? But we also have exponential decay. And so just to make sure that you remember, we don't always have to grow necessarily. Sometimes we start high and we actually get lower and lower and lower and lower and lower, approaching 0, but never touching, right? So this is exponential decay, and we have exponential growth, right? Exponential growth goes off to infinity. Exponential decay comes down and starts approaching 0, never touching. Okay. All right, last subject here before I wrap this up is the complex numbers, right? This follows our understanding of factoring and geometric series for the following reasons. So complex numbers. All right, this is I, right? The complex number I. Now, these are introduced because sometimes we can't factor. Sometimes we can't factor, okay? Remember, we're trying here to multiply to our final number, but add to this middle number. And 1 times 1 is 1, but 1 plus 1 is 2. And so we're stuck. We can't factor this, okay? Now, when that happens, fortunately, we have a nifty formula called the quadratic formula. And so if we have a quadratic, a degree 2 polynomial, then we have this nifty formula where the zeros occur, right? Zeros occur at the following x values. To calculate it, we have negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Ooh, bit of a mouthful, right? Those letters refer to the coefficients, the numbers in front of each term. So the number that appears in front of x squared is our a. The number that appears in front of our second term is our b. And this last term is our c. Okay? So we've run into an issue. We don't know how to factor this. Fortunately, we have the quadratic formula, which will tell us where this graph crosses the x-axis, right? Where those x values are. And we just need to plug in our a, our b, and our c values in order to calculate it, right? So you can see a equals 1, right? There's an imaginary 1 here. B equals 1 as well. C, in this case, also equals 1, right? Maybe I should choose different letters, but I mean different numbers, but this is kind of the classic example. So we just plug these into our formula. So we have negative b, or negative 1, plus or minus the square root of 1 squared minus 4 times 1 times 1 divided by 2 times 1. We can simplify this. We're left with negative 1 plus or minus the square root. 1 squared is 1 minus 4 times 1 times 1. So we are left with negative 3 divided by 2. All right. Now we have two scenarios. You can see we can split this up into one scenario and a second scenario. First, we have negative 1 plus the square root of negative 3 over 2. In the second scenario, we have negative 1 minus square root 3 over 2. Okay? That's what that plus or minus means there. Now we have a problem, though. We are not allowed to take the square root of a negative number, right? A square root means, what is the square root of 9? It means what number times itself is going to equal 9? Well, that's 3 times 3, right? Even negative 3 times negative 3 would work, right? Because negative 3 times negative 3 is positive 9. So what number times itself is going to equal a negative 3 or any negative number? Well, it's not possible, right? It's not possible. And so we introduce this new idea, that we call the number I. We say that I squared equals negative 1, okay? I squared equals negative 1. So I times I equals negative 1, right? I is equal to the square root of negative 1. I squared equals negative 1. I cubed is the same thing as I times I squared. So that's the same thing as negative the square root of negative 1 times negative 1, or negative square root of negative 1. And I to the fourth is positive 1 because I squared times I squared is I to the 4th. Negative 1 times negative 1 is positive 1. Okay, so the rules of I are as follows. I equals the square root of negative 1. I squared, by definition, must be negative 1. I times I is negative 1. I cubed is I squared times I. So we have negative square root of negative 1. Right? Square root of negative 1 is I. And so we actually write that I cubed is the same as negative I. Right? And I to the 4th equals positive 1, because that's just I squared times I squared. Right? Negative 1 times negative 1. Those are our rules of I. Now, we're able to actually analyze these two scenarios, scenario 1 and scenario 2, because now we know how to take the square root of a negative number. So scenario 1, we have negative 1 plus the square root of negative 3 divided by 2. Okay. The square root of negative 3, we could rewrite that as the square root of negative 1 times 3. Right? We know now that the square root of negative 1 equals I. Right? The square root of negative 1 is equal to I. And so the square root of negative 3 is I times square root of 3. Right? When we split this number up into two components, we know the square root of negative 1 is just I, and we're left with the square root of that positive 3. Okay, so any square root of any negative number, right? Square root of negative 10, that would be equal to square root of 10 times I, right? The I takes care of that negative. Okay, so we have negative 1 plus and lastly, we just want to split this fraction up. Anytime you have a sum or a difference in the numerator and only a single denominator, we can split this fraction. So this is equal to negative 1/2 plus the square root of 3 times I over 2. Okay, and so this is one location where our graph is going to cross the x-axis. Okay, now this number looks a little freaky, a little crazy, not something that we're used to, right? This is an imaginary number, right? We have a real part, right? We recognize negative 1/2, and we have a non-real part. This number I is in this part. So we have a real part and a non-real part. Non-real or imaginary, right? So how would we graph such a thing? Well, we return to the coordinate plane, but this time we have the imaginary plane. We have imaginary numbers as our outputs, and we have real numbers for input. So to graph this number here, our real part is negative 1/2. Our imaginary part is square root 3 divided by 2. So somewhere up here, square root 3 divided by 2. So that point would be right here. Okay. So much involved right there. But this idea of the imaginary number, it comes from factoring, right? It comes from when we try to factor and we're being asked to use the quadratic formula because there's no obvious technique that we've learned that's going to give us the answer to this polynomial. Once we start trying to determine what the zeros are by using the quadratic formula, sometimes we're left with a negative square root. And we're not allowed to have this, right? And so we run into another problem. And this is the point where imaginary numbers are introduced, this number I, where I is equal to the square root of -1. This gives us the ability to go ahead and continue solving the problem, right? We're not supposed to take the square root of negative numbers, but now that we've introduced this technique using the imaginary number I, we can go ahead and do so. We simplify down until we can't anymore, and we solve. And our answer should always be in two parts, a real part and an imaginary part, right? That's achievable by splitting the numerator into two parts, right? If the numerator is a sum and there's one number in the denominator, we can split that into the sum of two fractions, okay? When we're dealing with imaginary numbers, that's always going to be a real part and an imaginary part. To graph this information, we use the coordinate plane that we're used to, but instead of x, y, we have imaginary and real. You put your imaginary component up, down, right, as your range, and you put the real component left and right as your domain. Okay. We looked partly at the relevance of this and saw that some beautiful patterns are found and can be created using information like this. Answered questions that puzzled people for decades, like, is there a pattern or a reason between that phone interference going across electrical signals happens, right? Why is there the random or apparently random interferences on phone calls? By employing computers and understanding some of this mathematics, people were able to find out that the patterns are not random. In fact, they're can be predicted using different mathematical models. It was only made possible by the understanding of this information here. Okay, I'm losing a little bit of steam, so I'm going to stop right there. We will get into exponents next time, okay? But there we go. Some complex numbers, factoring, and geometric series. All right. We'll see you later.